Thank you.
Yes, we stay at this topic, mixed mode, variable mode mixity. We are dealing with that subject for a couple of years, trying to find out something on how crack driving forces and crack growth directions and so on. And as it is always the case, the work has been done by my PhD student, Heather Hosch, and especially here in this presentation by the group of Professor José Freire from Rio de Janeiro, which I appreciate very much. And I have the pleasure to come to nice places like here and talk a bit about these results. So what we did is that we made some experiments on these type of specimens. These are thin-walled tubes, and they have been loaded under cyclic tension and compression. And I apologize for my small numbers here, which you might not be able to read. However, as I did not travel by airplane, I dared to take with me one of these specimens in my car. I wouldn't allow me to take it in the airplane or whatever. So I think you can watch how it looks like, and this is one of the specimen. I cut it out from one. So we loaded it, for example, under pure tension, under pure torsion, cyclically of course, and then also under proportional loading with some numbers of torsion moment and normal forces. Then with a 45 degrees out of phase loading of these load components and a 90-degree out of phase loading. All our experiments have been performed under a load ratio, R ratio of -1. Nothing else we will hear today or see today. So we use digital image correlation to look what happens at crack tips, and we collected a large number of data, looking, for example, like this. The left-hand side, these are plotted the strains in the local y direction. Here, from this position, the crack initiated naturally. There was no pre-crack, nothing, except that notch, that artificial notch to initiate the crack, and then the crack grew wherever it wanted to go to. And of course, this red area here, these are fictitious strains because this evaluation ignored the existence of a crack. And, it's an indication of crack opening only. On the right-hand side, the shear tensors components, epsilon xy, are plotted here for the same instant as on the left-hand side. We collected such data during cycles. There have been many cycles without data collection, and after 500 or 1,000 or so cycles, we introduced 3 cycles with measuring. And just to give you an impression how it looks like, if you move this together into such an animation, you see the crack now closes here, and when the normal forces and torsional moments increase, it opens and then it closes again. You see that the closure starts here and propagates to the crack tip. Here's the crack tip, and then it opens again here. Now, and then opening proceeds to the crack tip, and ahead of the crack tip is maybe real strains in the material, and behind the crack tip these are these pseudo strains. This is crack opening. So, as I mentioned, we want to find something about crack driving forces. What makes the crack drive? What is its rate and what is its direction where it goes to? And then José Freire had the idea, let us take some of the well-known mixed mode criteria and try to apply them in a certain sense. And what you see here is a sketch of a crack. And here's a crack tip. You have here the global coordinate system xy and the local one, which is orientated along the crack tangent line of the crack tip. And José and his crew took some points, evaluation points on the crack flank A and B, and measured here from the digital images which we took, the relative displacements of these 2 points on the crack flank, and he played around a bit with the distance, and we had that presentation yesterday, thank you. Not so comprehensive evaluation as you did, but he played around to find an optimum where to position these points A and B to get a more or less distance-independent value of what is shown here in these equations. So what we have here is a crack opening displacement in the mode 1 and in the mode 2, and also, which is new now, in the mode 3 direction. And if you have seen the specimen itself, you see that there is obviously also in our experiments mode 3 contribution present. So we took the Williams series and resolved them with respect to K, and the input are these crack opening displacements in mode 1 and mode 2 and mode 3. So we have all these time steps where a snapshot was taken of the deformation field. We have now calculated values of that. However, keep in mind that in these measured values, CODs, if there is some plasticity around the crack tip, then it is incorporated in a certain sense in that values. And if there is crack closure, and there is crack closure, then these calculated K values are also some virtual plasticity and closure corrected K values, not strictly those from linear theory of elasticity. So this is, for example, one of these output sketches, and you see in red, here you have 3 cycles of the normal force, and in that magenta, dark magenta, this is the torsion moment here, and you see these are now the 90-degree out-of-phase loading, or specimen 31, 90-degree out-of-phase loading, and the rest of the 3 lines are these Ks, these calculated Ks, K1, K2, K3. K1 is the black line here, you see here the peak, and here it's on pink. This is the valley, the peak, the valley, and so on. The blue line is mode 2 and the green line is mode 3. You see in these calculated Ks that there is no longer a sinusoidal function over time as it is given, predefined by the loading, which is an indication of some kind of nonlinearity, be it plasticity, be it crack closure, or what it will be, a mixture of both. So you can take out of these graphs ranges of delta K, 3, delta K1, delta K2, and so on. And you see this is the outcome, one example of this outcome. So there are very many mixed mode hypotheses, and we took the first 2 which we could get, Erdogan and his colleague. We know all these formulas, and as we are now aware that we have to deal with K3-2, we found a hypothesis going back to Schöllmann and Richard and this crew in Germany in Paderborn. And these 2 have been evaluated a bit closer, and we had to extend it in a certain way to deal with this variable mode mixity, which we call it. So this original hypothesis, the mode mixity was constant during the cycles, and however it is not the case in our investigation now. And the idea of José Freire was now, for example, to extend the Schöllmann hypothesis in a certain way. In order to do that, you can introduce some abbreviations which are written here and rewrite that Schöllmann criteria like this. And you can therefore calculate at each time step j, you can evaluate this equivalent k of Schöllmann or so, and then you have at each and every time step you have a k, and then you can make a maximizing with respect to the time steps and with respect to the angle where you are investigating to find out some maximum value of such an equivalent k, taking all modes and time steps into account. Well, this is first of all a plot of the evolution of K1 over K2, keeping out of investigation K3, which is present 2. Please, if you see this specimen, keep in mind when the crack initiates, so this evaluation starts at the cycle number 7000 and something. When it initiates, it is under pure mode 1. There is a notch roof, a circular notch. There, no matter what load you apply, nominal forces or torsional moment, at the notch roof you have a uniaxial stress state. And the crack initiates there somewhere where the stresses are highest and grows first of all perpendicular to the notch root tangent line into the material, and therefore the start of all this is here with no K2, only K1 and K1 cycles here, maybe between -5 and 5 megapascals or something like that. And as the crack grows longer, then mode 2 creeps in. Creep is a wrong term, it comes in smoothly, and K2 increases, and here after maybe 14,000 cycles you have a considerable amount of K2 already present, and also, as I mentioned, K3. So this is the evolution of all these delta Ks, 1, 2, 3, as indicated previously. So 1 is this line here, blue is K2, and in the proportional case, K3 remains small compared to the other cases. And these Schönmann extended delta K equivalent also, these are these top lines. And you see that Erdogan and Schönmann do not deviate too much, which is due to the small contribution of K3. They are more or less identical, unless the cracks become long and you have a difference by the larger K3 contribution. However, if we now investigate the predicted angle and the orientation of the real crack where it grows, then there is a considerable difference. So we would have expected for this proportional case something around 40 degrees. And however, we found in our experiment only something about 20 degrees, which means that we have not found the final solution for this problem, and work must continue in a certain way. So this is now the result for the 90-degree out of phase loading. Again, the crack starts with a pure mode 1 loading at the notch root crack, the short crack in the notch root, and K2 comes in. However, now these both quantities are no longer proportional or so to each other, and there appear some arbitrarily, you might think, shaped contours in these plots. So if you plot now these delta Ks over the crack length, you see again delta K1 is small markers, it's the black dots here, and K2 are the blue dots, and the light green dots are the K3 contribution, and K3 is remarkably high here in these investigations. So the equivalent delta Ks, Schönmann extended Freire, I would like to say, are now the red triangles here on top, and the Erdogan-C version are the crosses here, a bit smaller now. Maybe you want to remember this number for a crack length between, let us say, 4 millimeters, measured from the notch root, to 6 millimeters. So these delta Ks remain clearly constant, and they are in the order of 40 megapascals square meter. This is what we came out from this measurement and evaluation, which I tried to explain. So now the orientation angle of the growing crack, it remains straight at the direction of 45 or so degrees, and you have seen in my animation that there is some pink angle at the distance of about 11 millimeters, and another one appeared at 15 millimeters. And what would have been predicted by these hypotheses, as we are using them now, you see, okay, there is an inherent amount of scattering, okay, and at least these criteria would predict some kinking into a different direction. So, however, there is no perfect match between what we measure and what we could calculate with this state-of-the-art, our state-of-the-art hypothesis. So now some final words on modeling. So this is now work of Dieter Hosch, who tried terribly to get that into finite elements. And first of all, we modeled the actual crack here now for the 90 degrees outer phase situation, where the crack grew down there, for example. And we assumed that at the opposite side, which is not completely true, you see also on the specimen, we assumed some symmetry and investigated what is going on with the kink angle here and so on and so on. We applied cyclic plasticity model from the model 1 type in order to get ratcheting and so in a acceptable way. And we set up a node release scheme, so we started without crack, and here at that facet here, we opened the debonding of nodes further and further with large steps, and Professor Antunes would be not very familiar with our node release scheme because it was much too rough. However, we had to arrive at some result, and one of these results could be expressed in this way. And here there is plotted the normal force over the torsion moment, and the 90-degree outer phase loading produces an ellipse in this graph. And we have indicated here the portion of the cycle where the crack is closed in this dark blue color, closed. And when the crack is open, these are the hollow symbols here. And closure also is defined if any node in the crack flank gets into contact. We say it's closed. And then the same in the experiment here. If Hosch or Jose finds any closure when evaluating these digital image correlation figures, then they say it is closed. And if we compare these two figures, we can say, okay, there is some similarity. Again, it's far away from being perfect. The point is that in our simulation, the crack is open for a longer portion of the cycle than it is for measured in the experiment. I might have forgotten that we did not take into account any friction so far. Maybe it's a problem of friction, but there are many other sources of errors when you do finite element-based node release schemes, plasticity, element size, and so on and so on. So it's certainly a contribution, but not a lot. So then in Urbino, I was still a fan of delta J integrals instead of Erdogan G or something like that. And still I forced Dieter Hosch to calculate cyclic J integrals. So this is the J integral formula from static fracture mechanics, and we took that in the extension of Dowling and Wüthrich and others. So we define a reference time frame where we say, okay, from this time frame on, we say what is going on. We found that the changes of the continuums, mechanics, quantities, stresses, strains, displacements. We calculate this integral. And if we do so, we have to find the starting position and the end position. And if you have found the starting position from that point on, the J integral evaluation would continue to increase, to have always higher and higher with the time step growing J integrals calculations. Then we trust them. And then in these cyclic cases, you arrive at a maximum, and then cyclic J integral goes down, and we say that the range of J integral is then here from here to there. Finding this initial point was not so difficult. It is always around somewhere where the crack opens. And as soon as it is completely open, or slightly before or behind that point, you get increasing J integrals until you get some decreasing value. So remember this number. For here the crack length of 5 millimeters, we arrive at the delta J effective value of 4 Newton per millimeters. Keep that in mind. Here it's again plotted. So what is plotted now here are the crack growth rates from the experiments. We observed the crack growth rates, and they are plotted now here over a delta J effective value. This value of 4 is the one I have shown just a slide before. And here you find values for a simple mode 1 case, so normal forces on the specimen, and then the crack growth. You see that crack growth rates are in the order of 10 to the power minus 3, so they are very quickly growing cracks. And well, the points gather around this area, which are marked with a green ellipse, and there is a straight line. This straight line goes down to 10 to the power minus 5 millimeter per cycle at the delta J value of 0.4, and at the rate of 10 to the power minus 1 millimeters per cycle, you usually end up with a delta J effective of 40. So this seems to be, for me, a law of nature, something like that, and I check literature always whether this is inconsistency with that values, which is for steels, especially also for this lower strength steels which we are dealing with. This is what we can find everywhere. So this is the line we would have expected, and for the pure mode 1 cases we are very confident and glad with our findings. Okay, everything seems to be okay. However, now if we go to this variable mode mixity mixed mode cases, we arrive at 4 newtons per millimeter at a crack growth rate of 10 to the power minus 3, and so we are far away of what I would have expected. So, the J effective at the moment is out of the race. So, remember this number of 40 megapascal square root meter from the Frere evaluation. So I have inserted a new abscissa here, and well, delta K with its indices here, I explained that, and the connection between the two axes is the usual K square over E prime. So if you are here at 30, make a square, you are at 1000, divide by 200,000, then you arrive here at 5 Newton per square millimeter. So if I would have plotted the same rates over delta K according to Frere's Schönmann extension, I would have ended up at this elliptical point, and this is a bit promising now for me. Maybe we are searching now in the right direction to get all these things matched. So this is an intermediate state of investigation. Next is that we will try to plot all our measured rates together with this new criteria and see whether we come up with a uniform scatter band or something like that. So this is the end of my story. The investigation is devoted to the search of fatigue crack driving force under non-proportional mixed mode conditions. We have measured crack growth rates experimentally in thin-walled tubes. We measured some deformation fields around using this digital image correlation technique. So we came along with a hypothesis based on, I call it now near tip crack flank displacement, which is suggested as an extension of Schönmann's mixed mode hypothesis, and the other hypothesis based on the J effective was also checked. However, this effective cyclic J integral works well for pure mode and fails for its non-proportional mixed mode conditions. And the new one is promising, as I mentioned. So the outlook is much work has to be done. For the initial work, we got some funding, which we thank for, and I thank you for your attention.